world exist far above the planet. Our job? To launch the smartest solutions, to protect our satellites, clean up our clutter, to propel breakthroughs in propulsion, to learn more about our place in the universe, to outpace emerging threats. Every day, the Aerospace Corporation uses the latest technologies to ensure our nation's safety and leadership in space.
The Artemis program is critical to the future of humanity. We are landing the first woman and next man on the moon.
The architecture is really comprised of three major elements. We, Lockheed, are building the ascent element. It's where the crew is housed.
The transfer element is to transfer the lunar lander down to the surface of the moon.
The descent element, built by Blue Origin, is really a game-changing moon landing vehicle.
As a partner in the national team, Draper will provide guidance, navigation, and control, avionics, and software systems.
And in order to pull this off, it takes a team.
We are designing a vehicle that will be able to ensure humanity has a permanent presence on the
moon. Okay, and welcome back, everybody. It's good to have you back in this session. So our next session for the day is talking about Artemis and sustainable lunar exploration. Thank you again to our day one sponsors, the Aerospace Corporation, Blue Origin, and the Boeing Company. So our moderator for this panel is Doug Craig, Strategic Analysis and Planning Manager at the Human Exploration and Operations Mission Directorate at NASA headquarters. So Doug, turn on your video and take it away.
Okay, thanks, Jim.
Yep.
So it's great to be here. So we heard in the HLS panel session the importance of having a sustainable lunar exploration plan. So what you're going to see with this panel, we have a very distinguished panel here. We're going to go through and kind of lay out a strategy for sustainable lunar exploration, and we'll actually, most of the speakers are from NASA, with Clive Neal as being the one outsider, but he'll give a good perspective on the lunar asset. So with that, let me go next chart, please. Next chart. Okay, so today's lineup, you see here, I'm Doug Craig. I'm from NASA headquarters in the Human Exploration and Operations Mission Directorate in the SE&I area, where I'm responsible for strategic analysis as well as for program formulation. Next, we have Ginger Flores, and she's going to be talking about habitation systems. Mike Gernhardt's going to be talking about mobility capability required for the sustainable exploration. Christina Koch is going to be talking about kind of a new way of designing systems, operationally driven designs. Clive Neal, as I said, is going to be talking about having the moon as an asset for us, and how we need to take advantage of it to become sustainable. And then Michelle Rucker is kind of all things Mars, and she is going to be talking about how the lunar environment is a great place to do testing for Mars systems. So I'll introduce them a little bit more when we get into their sections. If you go to the next chart. So I wanted to kind of set some context for you. So if you remember, Space Policy Directive 1 basically stated that we want to lead the return of humans to the moon for long-term exploration and utilization, and then followed by human missions to Mars. So this is very important. It's not the moon and not just Mars, it's both. And basically using the moon as a testing area for Mars. If you go to the next chart, please. So you remember Vice President Pence came up and stated that we're going to be landing the first American woman and next American man on the lunar surface in 2024. and then develop a sustained lunar presence by 2028. And so basically it's what follows the 2024 mission, and that's what we're going to be talking about. But it's very important that this isn't a one and done deal, as was stated earlier. So if you go to the next chart. Okay, so this, you've probably seen these charts before, but I'm going to go into a little bit more detail. So this is the chart for the run up to the mission in 2024. So I'm not going to get into that. That's basically what you heard from the HLS program panel. If you go to the next chart, I want to focus more on what do we do after we've gone there. And so, as I said, there's really two major objectives after the 2024 mission. First is setting up a sustained lunar presence, and then using that lunar presence as also as an analog for Mars missions. So let's define kind of where we're headed with the sustained lunar presence. What NASA's looking at for a sustained lunar presence is landing 4 crew on the lunar surface for 30 plus days missions. To do that, we're looking at having a habitat as well as a pressurized rover to have mobility. So how are we going to get there? So there's a kind of a strategy with regards to how we deliver the elements, and there's actually purpose behind the delivery schedule. So let's start from the left side, where we're going to first, the gateway is going to be going up to lunar orbit. We're going to have an international habitat delivered up there. So for the first missions, it's going to be able to help with the logistics as well as be comm relay, and to do logistics transfer to the HLS systems. In the same time frame, we're going to have a lunar terrain vehicle that's delivered to the lunar surface. So this is a non-pressurized rover, and it's basically for crew members in EVA to get onto the moon and be able to rove farther than the 1 to 2 kilometers away from the lander. Next up, we're going to expand Gateway with robotic systems as well as other international provided systems. And then we're going to have kind of the pressurized rover land on the surface. And that will enable 2 crews a crew of 2 to go even further away from the landing sites, especially having the LTV following as a kind of a contingency / support vehicle. We picked the rover going first so that when we have the landers come for future missions, that the rover can drive up to it and then transfer the crew to other assets as required. And so the next asset is the surface hab that will be delivered. And then that will enable us to send 4 crew down for 30 plus days. It's also important that we're going to have logistics landers to be able to support the logistics required for these 30-day plus missions. Power is also going to be important, so we're looking at a fission power system landed. It will also support the ISRU plants. So one of the things I didn't mention that during this buildup, there'll be 2 different ISRU technology plants that are landed and tested out. One of the key objectives of the sustained lunar activity is to research the what types of in situ resource utilization activities work the best and have the best potential for moving out. And then once we get those on the surface, what we're looking at doing is providing an enhanced habitable capability delivered to Gateway, which will extend the durations in space to much longer than the 30 to 40 day missions that we would have without it. This will enable us to start testing out systems and as well as the humans to make sure we're prepared to go for a 3-year mission, 2 to 3 year mission to Mars. And then we'll also be landing an ISRU pilot plant, which will basically be selected by the 2 technologies. We'll take the lead technology from those 2 and develop an ISRU pilot plant and use this fission surface power for them. So that's kind of the strategy in a nutshell. If you go to the next chart, basically wanted to just say that if you hear the term Artemis Base Camp, that's what we're looking at pulling together for the South Pole. And that's what, once we get the Artemis Base Camp operational, that will be kind of when we feel that we've become having a sustainable lunar presence. So with that, the next presentation we'll go to go to the next chart, is Ginger Flores. Okay, so she serves as the Habitation Systems Development Manager at Marshall Space Flight Center there in Huntsville. And she provides the leadership for the center activities in support of the Gateway, as well as the focal point for habitation development activities, managing strategic partnerships with commercial habitation system providers, and leading the early formulation of lunar surface and deep space transit habitats. So with that, Ginger.
All right, thank you, Doug. I am very honored to be here today. Let's go to the next slide. All right, so a central theme through all human architectures is the need for safe and reliable habitation systems. We want to keep the crew happy and healthy and productive at every exploration destination. These habitation capabilities provide a home away from Earth for the crew, and they need to be able to support all the equipment and consumables for the mission. This includes a breathable atmosphere, drinking water, food, areas for work and exercise and play, sleeping quarters, and hygiene requirements. NASA has placed a high priority on commercial partnering approaches for the development of these systems. And over the last several years, we've utilized the Next Step Appendix A. This is under the Next Space Technologies for Exploration Partnerships, BAA. And this approach has been a true enabler for innovation and collaboration between the NASA team and industry. The pictures on this slide represent one of the successes and highlights of Phase 2, which was the extensive crew evaluation of each of the partners' very diverse, high-fidelity ground prototypes. Next slide. So that Next Step habitation work has progressed through several phases. It began in Phase 1 with development of contractors' unique design and operational concepts focused on the Lunar Gateway. In Phase 2, they continued to mature those concepts and develop ground prototypes, culminating in the crew evaluation and testing. This phased approach ended up providing significant benefits back to NASA when the decision was made to leverage Northrop Grumman's Phase 2 work. A contract was initiated that began development of the HALO, or the Habitation and Logistics Outpost, on a very aggressive schedule. HALO is a small habitable volume for the early gateway, and it will accommodate docking. It will also provide additional services such as life support, and will serve it as an initial backbone for avionics and software, power, and comm until the international hab arrives, which is being provided by our ESA partners. So we're now in Phase 3 of Next Step, where we've continued to advance gateway requirements and system definition, but we have also pivoted the focus to lunar surface and deep space habitation. Next slide. So with SPD-1, as Doug mentioned, the agency started formulating a strategy to achieve a sustained lunar presence. In order to meet that directive, the capability for long-term habitation is required. The Foundation Surface Hab, or the FSH, is the current concept that's in consideration to serve as this initial surface element. and it will enable extended crew mission durations. It will provide habitability for 30 to 60 days for a crew of 2 to 4 and accommodate crew systems like a galley, their quarters, exercise, medical station, and personal hygiene. With longer mission durations and a high demand for EVA, we'll need the capability to perform suit maintenance, which will also be provided. In addition, the elevation of the FSH will benefit both solar arrays and communication systems, making it an ideal hub for power and comm. A core element of the sustained lunar presence is feeding forward to Mars with the expansion of habitation capabilities for deep space. Next slide, please. So the Enhanced Habitation Capability, or EHC, concept focuses on the development of a habitation module capable of keeping the crew healthy and productive during long-duration deep space stays. And these will be in the order of years versus months. This is a larger volume, about 300 cubic meters. Think about a large Winnebago compared to the Lunar Hab as the smaller Airstream. Inflatable, metallic, and hybrid structures are all in consideration. There are various options being traded within our Mars architecture studies to determine the best approach for development and deployment. As Doug mentioned, one option is to deploy an EHC module to the gateway where it could be wrung out and fully outfitted. This approach would allow the crew to perform multi-month operations and tests that could serve as analogs for future Mars missions. It could also be integrated with a prop system at a later time and go on to Mars or other destinations. Another potential option is to deploy an early EHC to LEO as a test bed for deep space. And an advantage of this approach would be that it would allow more frequent logistics and crew deliveries. So we're studying multiple approaches for an EHC to be used for Mars shakedown missions with the ultimate objective of serving as a Mars transit hab. Next slide, please. As NASA takes on the challenge for the first time of establishing a habitat on the moon and a habitat without resupply opportunities in deep space, there are numerous technical challenges that we have in front of us. Some of the big ones, landers and in-space propulsion systems, will be design drivers for FSH and EHC respectively. We're currently working to identify cargo needs specific to HABs to the lander team. Launch lift capability and fairing constraints could also drive designs for both habitats. And we'll need sufficient stowage volumes to accommodate the required systems and the consumables, which take up a lot of mass and volume and can vary depending on mission duration and destination. ECLS especially is a significant driver, as a design solution can consume significant mass and volume, but inversely, it has the ability to reduce resupply demand. Mars ECLS will need to be highly regenerative to account for lack of resupply. So these missions are the real payday for NASA's advanced ECLS investments. Next slide. So the central element of a sustainable human presence in space is the development of habitation systems that will not only extend operations, but keep the crew safe and healthy throughout. We're continuing to work closely with industry to develop the first lunar habitat and enable human exploration of deep space as we prepare to voyage to Mars. Thank you. Back to you, Doug.
Okay, thanks, Ginger. Okay, so that was the habitation section of the sustainable lunar presence. So now we're going to go into the mobility aspect of it with Mike Gernhardt. Mike Gernhardt has extensive experience in subsea construction and robotics and founded the company Oceaneering Space Systems. He's also a NASA astronaut and did 4 space missions, including the first spacewalk from ISS. He's currently leading the Lunar Human Mobility Systems at NASA. So, Mike?
Okay, thank you, Doug. Next slide, please. So let's start out with the benefits of an unpressurized rover and what we learned from Apollo. And if you look at across the 6 Apollo missions, the first 3 were walking. Apollo 1 was only 62 meters from the lander. Apollo 12 was 450, and then Apollo 14 was 1.4 kilometers. Basically, if you look at the number of samples, they start going up a lot once we added the LRV. And it's not just the number or weight of samples, it's the number of geological units that you can traverse to that tells you so much more. And so basically, there was some famous scientist whose name escapes me that said that 9% of the good science came after we had the LRV. So it not only gets you to different geological units to select a greater diversity of samples, it also helps you carry, if you look at the bottom line, more tools in sample or more tools in specialized tools to collect samples versus what you can just carry on your suit. Okay, next slide. This is kind of a big picture of Apollo 14, which did about 1.4 kilometers. And what you see on the right is the traverse path of one of the Apollo 17 traverses. And there's so many more discoveries that can be made with longer traverse distances. And if you look at the inset, you see a bunch of different colors. And if you look really close, there's a radius that with a 2 kilometer walk back, which is what we are saying for EVA, versus a 10 kilometer. And depending on where you land, if you only have a 2 kilometer walk back, you might be within a single geological unit. Whereas with the 10 kilometer range afforded by the LTV, you could get up to 4, 5, or even 6 different geological units. Next slide. So what is the LTV? In concept, it's very similar to the LRV and Apollo, but will probably require some different general arrangements to address the unique aspects of operating at the lunar South Pole. And these are just some concept drawings that don't reflect our designs or for illustrative purposes only, but we're doing all kinds of risk reduction trades, looking at how you seat the crew, how you might provide artificial lighting for the downsun work at the South Pole, as well as possibly sunshades for the upsun work. Some of the other differences and capabilities between the LTV and the LRV are that this will now be reusable and rechargeable with a service life of up to 10 years with planned upgrades and maintenance. It'll be capable of remote operations from the HLS gateway and Earth. We will be able to move the LTV from one landing zone to another to support that. As we all know, the early missions will only be about a week, and even the mature missions are only going to be 60 days. So, there's 50 plus weeks to do other things. And so we're envisioning that the LTV will interface with a variety of science instruments and payloads that allow us to have this really capable vehicle that's probably at least 10 or 15 times faster than previous ones like the Viper and so forth. And then also we need to survive eclipse period. So there's some technical challenges with the LTV. Okay, next slide. Additional other use cases that we're studying, and none of this is in cast in concrete, but I talked about the science instruments, support resource mapping for multiple customers, including the USGS, scout landing zones. And another really big advantage is that with the LTV up there, we can scout the traverses that we want the crew to do when they get there. And so the crew can actually train on their very specific traverses and know them like the back of their hand. And of course, still have the ability to deviate based on their scientific judgment. Without reading every one of these, logistics are a big challenge. And Ginger mentioned that. And unlike space station, these logistics are not delivered to the point of use. We're not going to have something that flies up and docks with the foundational surface hab or the pressurized rover. So we see a role of the LTV and transport a variety of logistics from their landing site to the point of use. We probably will need some auxiliary power to make it through the night. And we have this concept for a portable utility pallet that has at least 200 kilowatt hours of energy storage in the solar array, many other things. And as we go forward to look at infrastructure for sustained lunar presence, we need to deploy cables to distribute power. We might need earth movement equipment and things of that nature. So there's a lot of things that the LTV can do, and it's actually going to be a big workhorse in the Artemis infrastructure. Next slide. And then, as Doug mentioned, there's the HMP, formerly known as the Small Pressurized Rover. This is a very unique capability that's enabled by the exploration atmosphere, which is 8.2 psi, 34% oxygen. That allows us to use suit ports so the crew can jump into their suits with essentially 15 minutes of pre-breathe and go out and do short EVAs as needed. There's a lot of other features of this I won't go into, but it's got a radiation shelter. It has more in common with a suit plus than a HAB ECLIS system, so we use the same swing beds that allow us to minimize spares and so forth. Next slide. Years ago, 2008, we actually did a very rigorous test out in the desert to compare the performance of a crew in a pressurized rover versus an unpressurized rover. And I won't bore you with the details, but we had 6 geologists that scored us with very rigorous metrics, and they could care about nothing other than the rocks that we collected. And basically, we had 57% greater scientific performance with 61% less EVA time. So we basically proved without a shadow of a doubt that the small pressurized rover with suit ports was superior to an LTV. Next slide. There's also all kinds of health and safety benefits, including that you're never more than about 10 minutes away from a safe haven. So should you have greater than a spec suit leak, you can get back. There's radiation protection. You spend less time in your suit, so there's less suit-induced trauma. Whereas you'll go out with a full drink bag and a diaper, you probably won't use them. Anyhow, there's a lot of advantages here. Next slide as we come to the end here. So one of the challenges that we have is to now work with the science communities to do a deep dive into traverse planning to develop options of how we use a combination of the HMP and the LTV together to exploit the advantages of both. Doug alluded to the fact that if the small pressurized rover fails, we could have the LTV drive us back to the lander, which would be about 20 kilometers, but we can also use the LTV to scout and things of that nature. So we're getting ready to do a deep dive and looking forward to working with the science community on that. And then the last slide to get off the stage here is this is planned to be an industry partnership. So we're going to have a phased iterative design, build, and test strategy with our industry partners that will really leverage the literally billions of dollars that U.S. industry has invested into battery technology, electric vehicles, autonomous driving, sensor fusion, and software. Thank you.
Okay, thanks. Thanks, Mike. So next up, we have Christina Koch. She is going to be discussing operationally driven design. Christina is a NASA astronaut who recently returned, actually just about a year ago, from 11-month stay on ISS. She has previous background as an engineer in space science instrumentation and remote science based field engineering. So, Christina.
Hi, Doug. Thank you very much for that introduction. It's great to be here, and I can take my first slide, please. So as Doug mentioned, I'm not an engineer or designer of the things that you've been hearing about, but I hope to be able to answer any questions that you have and provide insight on the idea of making sure that we fold in operations use while we're doing the designing to make sure we're not kicking that can down the road and taking away efficiency from those operations when they do get underway. I'm happy to report that that is a part of all of the design that you've seen so far, and I'm going to talk a little bit more about that in detail. Next slide, please. And do we have the next slide, please? I'm not seeing it. So the first way that you, oops, let's go back one if that's all right. And maybe there may be a delay. So we'll go to the slide that had all the photos. Great, thank you. So the first way that we can talk about analog or operational design is by using the many analogs that we have access to, because that allows us to build in the entire sort of system-wide effort that's going on to include a mission control, to include logistics, development of any waste that we have with our supplies, and how we go about our day, the daily flow, and the things that may actually open up based on when we utilize things on board and how we utilize them. So one example for that is that a lot of the folks that are designing, say, the tools that the astronauts will use as they're doing the geology on the surface of the moon have actually been involved for many missions in NEMO and have, understand sort of what goes into that. So those same people are taking what they've already learned on several NEMO missions and applying it, say, when they go to the Johnson Space Center rock yard with the actual tools and spacesuit elements that make that part of our design development more realistic. So analogs and using them to a really high degree early on in our design process is underway, and it's a big part of how we're going to make sure we're efficient once we get to the moon. Next slide, please. So we've talked a lot about logistics, and one of the differences in the ISS logistics that we have right now is that we have continuous habitation of the ISS, and we also have handover of crews. So there's an opportunity for a new crew to be taught by the crew that's there how things have been going, the most efficient way to do operations, and kind of where everything can be located and found. In a lunar model where we may only have missions, as you've heard, about 30 to 60 days at a time, we need to have more advanced and automated stowage capability so that when we arrive, we know exactly where everything is. There's a standardization of, say, package sizes, location coding, and things like that, how we go through the process of disposal and moving that cargo to where it needs to be utilized from where it's delivered. So that's one way that we're folding that in right now. Next slide. And as Mike alluded to, when these landers, the CLIPS landers, bring some of the logistics, we're going to then have to distribute it to where it's needed, either where it's needed for the work, if it's tools oriented, or where it's needed for actual consumption, such as food and provisions and supplies. So there's a lot of notional concepts out there being worked right now, including things like comparing the actual airlock that'll be on some of the habitation modules that Ginger talked about with our own airlock, and what do we already know about what will and won't fit, and how much additional time we might need to devote if we're moving big items in and out. So that's already, feeding forward into our lunar operations design. Next slide. So when we talk, kind of going to the next step, we've talked about where things are, how we're going to get them to where they need to go. Now let's talk about the end of that cargo life cycle in waste management. One thing that we have to work with in the lunar environment is the potential to do actually exterior waste storage. And in the upper video that you see, that's the closeout of a waste vehicle on board the space station, where we have a different model. We recognize that we have the Earth's atmosphere where our waste products can be burnt up as they re-enter. And so there's not as much of a need to have everything conform to certain standards in terms of the size of cargo vessels and things like that. We have the ability to kind of button everything up at the end and make it work and send the waste vehicle home. Whereas on the surface, we're not going to want to have, piles, for lack of a better term, of different sizes of waste materials and things like that. So we're looking at concept of using our waste materials as radiation shielding, and maybe originally it starts as food that we haven't utilized, and after it's a waste product, it goes back on the exterior side of a vehicle to provide that shielding. Also looking at just better ways that we can, based on what we know from our time in space, do bulk food provisioning instead of how we do it right now on ISS, where we have kind of the luxury of sending up individualized food packets and things like that, because waste isn't as much of a commodity. So next slide, please. Another aspect of operationally driven design actually is talks to how we posture ourselves in terms of spares management and repair. Currently on the ISS, we utilize an orbital replacement unit strategy, where if something breaks, usually a fairly large box of something, we go out and we replace the entire box. So that would be the picture that you see in the EVA there. As opposed to a strategy where we actually stock smaller component level things, and we have a training of the crew to allow for that, what we call in the current model, invasive repair and replacement of individual components, which we actually do occasionally have the opportunity to do on ISS, but it's a much bigger deal when we actually go into a box like you see Nick and I doing there and replace, say, just an electronics card. There's also a lot of talk about having, for example, our ECLIS systems. Do you have them be dissimilar in terms of redundancy so that if an entire concept of engineering doesn't pan out well, you at least have another concept to rely on? Or are they similar so that they can rely on redundancy and sparing? So we're taking a look at all those things and folding in what we've learned on ISS. Next slide. And then, talking about mobility like Mike did, of course, brings into play the talk about new suits. So the Exploration EMU is an exciting new spacesuit that will allow us to be much more mobile. It takes into account a lot of the things we've learned about extravehicular activities and how those are going to need to change. I think some of the really innovative things that I like are the torso movement to allow to actually, astronauts to be able to lean down, pick things up. Selectable pressure ranges so that you can operate much easier in a lower pressurized suit, but not all the time. So you're not increasing your pre-breathe options and things like that. And then, of course, one of the big gains in operational use is what Mike talked about, not needing that really long pre-breathe time before you do an EVA. And next slide. And I won't talk much about the pressurized rover that Mike introduced, except to just point out, of course, its huge advantage in being able to sort of climb in, not have a dedicated airlock. I really wanted to highlight the photo you see there of how an astronaut would actually ingress the suit. And then also point to the fact that it's already been identified we would still need an airlock for things like suit maintenance. You have to operate the controls of the suit when you're doing maintenance to it. So there are cases where you're going to need to actually be able to access the full suit. So I like that the designs we're talking about have all those capabilities. Next slide. And that's it for me. I'll pass it back to you, Doug.
Okay, thanks, Christina. Okay, next up we have Clive Neal. He's going to talk to us about using the moon as an asset. Clive has been studying all things lunar since coming to America in 1986 from the United Kingdom. He's a professor of planetary geology at the University of Notre Dame and is passionate about NASA and in returning to humans to the moon and beyond in a sustainable, economically beneficial, and permanent way. So, Clive?
All right, thanks, Doug. As the outsider here, I'll go quickly. You can tell from my Northern Indiana accent that I've been at Notre Dame for a long time now. So I want to talk about the moon being an enabling asset. We have a moon nearby as an off-world proving ground, and we've heard a lot about using the moon to go to Mars. And yeah, that's great. But the important thing is that the moon is a very interesting and important asset beyond just using it to go to Mars. It's scientifically interesting, and it has the potential to actually create jobs. As I work at a university, when I look at the potential of from the science data for new and exciting ways of doing things, I get excited, and then I look in the mirror and realize that I'm not a young man anymore, and it's probably living vicariously through my students as happens these days. But this is an exciting time because, as Doug said at the beginning, this is the moon and Mars. We're going out into the solar system in a logical, in a way that is going to be beneficial, and that word sustainable stands out, whereby we need to really think about, well, what do we mean by sustainable? Well, number one is to leverage from our systems architecture and development so that they work at multiple locations. We don't create destination specific architectures if you're going to go to multiple destinations, because it's not a good use of taxpayers' money. So looking at Artemis, then we need to be looking at that tangible return on the taxpayer investment. So this is the start of sustainability, looking at technological advancements that are going to be needed to allow humans to survive and thrive on the moon and Mars, that will have tangible benefits back here on Earth, that have a benefit both economically and maybe for society as a whole. So one of these in the job creation has already been alluded to by looking at in situ resource utilization. That's enabling for development. The Artemis can be enabling for the development of these local resources. And that's the exciting thing, because that means that we can leverage off the private sector that we have down on this planet. And we held a workshop in 2019, the Lunar ISRU workshop, and realized just how out of touch we are with actual mining practices. That was a big wake up call. But the potential that came out of for the moon for this development of ISRU and feed forwarding to other destinations such as Mars became very, very evident. Next time step, please. So the other thing that I want to talk about, if that's not coming through, press the button, please. So Artemis can be enabling for the rapid development of the cislunar economy. This is again making things sustainable because we're showing a tangible return on investment. So I would then push my NASA colleagues to say that foundational surface habitat, how is that going to evolve? How is it going to get so we can actually house people for longer, so that we can actually have on the lunar surface a Mars mission of 500 days? How is this evolvable? What is being built in to make it evolvable? And the other issue that being a geologist, I don't normally think about policy or legal issues, but these are things that need to be addressed and resolved. And I do like the Artemis Accords, because they create a starting point for discussion that actually has tangible things and specific things that need to be addressed. So I think we have a starting point here to set the precedent for getting these issues sorted out. And cooperation, not competition. Apollo was brilliant. We've heard a lot about looking at the achievements of Apollo just in this quick panel session, but Apollo was canceled just over 3 years from Apollo 11 landing because it was a competition, not cooperation. And once we'd landed Apollo 11, we'd won that competition. So we look at space station, and Christina can attest to this. This has been enduring through international cooperation. And again, development of the cislunar economy, if done properly and thinking, how is it going to evolve? We then set the blueprint for developing a cis-Martian economy that goes along with that, making not only the moon, but also Mars sustainable because of a tangible return on that taxpayer investment. So I think sustaining the sustainable human presence on the moon is a critical step for sustaining humanity out of the solar system, but also showing that this is not just a drain on the taxpayer, and we don't have this, oh, there's lots of problems down here we have to deal with. Why the heck are we sending humans to the moon? While we're doing it in order to benefit society back on this planet. And with that, I'll stop.
Okay, thanks, Clive. All right, so actually, Clive had a good segue into how the moon. One of the ways the moon can be used as an asset is to prepare for Mars. So next up, we have Michelle Rucker, who's going to talk about how that can be done, not just from the assets, but also from technology development and testing. Michelle is a 34-year veteran of NASA. She began her NASA career as a test engineer at White Sands Test Facility before serving as a systems engineer on the Space Shuttle and ISS. She currently leads the Human Exploration and Operations Mission Directorate's Mars Architecture Team, developing Mars human exploration mission concepts. So that, Michelle?
Thanks, Ed. You can go on to the next page. And so I have the best job at NASA because, as you just saw, everybody else is doing most of the hard work for me. Virtually everything that you just saw for the moon, even your stuff, Clive, will feed forward to Mars. So let's talk a little bit about that. So not just Artemis, but all the way back to the work that we're still doing on the space station. We got pretty good at doing vehicle in-space assembly, outfitting, refurbishment, things like that at ISS. As part of Gateway, we'll continue that progress, learning how to assemble and outfit complex vehicles. I was just thinking about we're coming up on the 20th anniversary of the International Space Station. And Mike Gernhardt and I actually started working together on the ISS before we even had humans up there. And Mike was one of the guys that actually physically bolted pieces together out there. So that whole vehicle in space assembly is a critical operation. We're gonna learn a little bit more about how to do that, not as close to home, where it's a little bit easier to get repair parts and things up, but a little bit further away. We're gonna put some time on critical systems, especially the life support system. That is a critical one. There's a lot of things you can do workarounds on, but if the life support system goes down on the way to Mars, that's gonna be a bad day. System repair even with in-space manufacturing, there's a lot of energy behind in-space manufacturing, not just the actual making of parts, but some of the post-processing. We're looking into that. Can we reduce our logistics and spares? The logistics and consumables planning, if you get halfway to Mars and run out of something, it's a bad day. You're going to have to figure out how to live without it or cobble it from whatever you have on board. So we're learning, we're actually data mining the ISS right now to understand the logistics and consumables, be able to plan out in advance. Right now on ISS, we have virtual on-demand resupply. We won't have that at Mars. We'll get to practice that at Gateway. The exploration food system, we're learning everything from longer shelf life to how to look at alternate packaging techniques, trying to make sure that the nutritional, the space food tends to lose nutrition over time. We're looking at alternative freezers for frozen food to try to keep food fresh for longer, things like that. Crew isolation and the health and performance, going from we've gotten pretty good at going from microgravity back to Earth gravity. We understand how hard that is on humans. We'll get another data point going from microgravity down to lunar gravity. Mars gravity is a little bit higher. It's not as high as Earth, but it's a little bit higher than the moon. So it gives us one more data point, learning how crew can readapt to gravity as they go back and forth between those environments. And then practicing crew autonomy. There's going to be a comm delay all the way to Mars, so we can practice that closer to home. Next page. On the surface, one of the things that we're looking at with the HLS landers is landing hazard detection and avoidance. Not just detecting and avoiding things that we don't want to hit, but we want to make sure we're not throwing rocks at other surface equipment that's already in place. Like I mentioned, the crew gravity readaptation, the surface mobility prototypes that Christina and Mike talked about. Ideally, those will be the same type of vehicle that we would take to Mars. We might need a little bit more energy for those since it's a little bit higher gravity, but we're going to learn a lot about how to operate those and how to maintain those, more importantly. The planetary suit experience, once you get back into the gravity field, it's a little bit harder hauling that heavy suit around. So learning how to operate in a gravity field will be important. In situ spacesuit and rover maintenance is important. Surface power, that's an interesting one. On Mars, so on the South Pole, we'll have a little bit of sunlight, but on Mars, there's a day-night cycle, and there's dust storms that can pop up and blot out the sun for a couple of weeks. So having a more reliable surface power system is important. So we're looking at a compact fission system that we would actually test on the moon so that we can validate it for Mars. That's an exciting new technology that's coming along. The ingress egress, trying to keep the dust out of your habitat. That is a bit of a nuisance on the moon. On Mars, it's a little bit different because we also have to worry about planetary protection. So in other words, we don't want any bacteria on the crew to contaminate the science. If we go to Mars to look for life, we need to make sure we keep those things separate. And if there is any life that we find on Mars, we want to make sure we don't bring it back uncontained to Earth. So that'll give us an opportunity on the moon to be able to practice and validate those planetary protection protocols. And then, of course, all the other science, the operations, the tools, the timelines, trying to perfect those operations in an operational environment. Yep, we do that on Earth. This is sort of the next level fidelity of operations testing that we can do on the moon. And that is it for me.
Okay, thanks, Michelle. Okay, So Jim, I guess it's time for questions. Any questions for the group?
Yeah, sure. Let's see. This one's interesting for Ginger. For Gateway, is NASA open to non-suit solutions or single person spacecraft for EVA?
Jim, I think I will actually throw that one over to Michelle, since this is a suit-related question.
There you go. Michelle, take it away.
The pressurized rover that Mike and Christina talked about, that essentially is that's a two-person personal vehicle. It is essentially a personal spacecraft. It's very small. I know there are concepts out there for single-person spacecraft. Those have been studied. They're not out of the realm of possibility. It sort of depends on what your mission objectives are, what you're trying to do. But yeah, I wouldn't say anything's been ruled out at this point.
Okay. Great. This one is to Christina. Is Christina still on? Yeah, I think so. So you were talking about the radiation shielding, and does that include all waste being used for radiation shielding? You might see where we're going with this one. Anything and everything available for radiation shielding?
So Jim, it looks like Christina had to drop
yeah,
out.
I'm sorry. It looks like she dropped out. Okay. Oh well.
No, but,
go ahead.
Yeah. So basically, we're looking at any waste that has hydrogen content, high hydrogen content, can be used for radiation protection. So that would be the kind of the types of waste we would be looking for.
Okay. This one's for Clive. What's a good historical analog to cislunar the cislunar economy development? Is there anything done before that's at all similar that we can look to?
Well, you look at supply chains, and then don't tax the hell out of it, because they'll put all the tea in Boston Harbor. Let's put it that way. There are examples in history that are replete with how not to do it. We learn from history, otherwise we're destined to repeat it. So the thing is that we go to the moon and we use the resources there. We need to understand if they're renewable. They're probably not. Then so how much are we going to recycle of those resources? There's a whole new technology that can be brought in that would actually help with closed loop life support and reaching that nirvana. So I think that we start envisaging things that we know, and just like low Earth orbit, we see where it takes us. And I think we need to be open to new avenues of investigation. And I think we need to be open to international cooperation, and also that we need to be open to the human mistakes down here when we've used resources maybe too much, and how we then can be better stewards as we go out into the solar system. So there are a number of things that need to be taken into account here, but the important thing is the potential is there. But we can only, I think we can only imagine just a little bit of the potential with the cislunar economy, let alone the cis-Martian economy. And we're planning multiple decades out. But hopefully my great-grandkids will see that. But what is being started here is something that has the potential to have unimaginable consequences and implications and benefits down here. But so thinking about that in the planning process and evolvability of systems and multiple use systems, I think that is the way we need to think about this now.
Excellent. Thank you, Clive. Michelle, nuclear. Yeah, right. Everybody's thinking about it, and nobody's really talking about it yet. So how critical is nuclear to a sustainable presence on the moon or elsewhere?
So for the surface, let's talk surface first, surface power. If you have lots of available sunlight and no eclipses, and you have plenty of energy storage, you don't necessarily need nuclear. If you're worried about an eclipse situation, or if you're worried about parts of the moon where you're not going to get much sunlight, nuclear becomes pretty important. For Mars, just look at what happened with the Polar Opportunity rover. That is one of my personal heroes, and that little guy was cranking along, and literally with its dying breath, it was sending us data about that really bad dust storm. And we use that data to size our power systems for a human mission, because we don't ever want to put a human in the situation that poor rover had to face, where there just wasn't enough sunlight. So for extrapolating out to Mars, it's pretty important, I believe, for the Martian surface power systems to be pretty reliable. We can augment with solar, of course. Fuel cells we're looking at. There's lots of options, but compact fission is probably a pretty good solution, and it's extensible between the moon and Mars. We can use it in a lot of places on the moon. So from a service perspective, it's very important for long-term sustainability, especially for the kinds of operations that Clive wants to do, where he's looking at resource utilization. Trying to extract the water from the minerals takes a lot of energy. And if you need a lot of energy, you need a pretty solid power source. For in-space transportation, nuclear is also in the cards right now. The Department of Energy and NASA just signed a memo of understanding just a couple days ago to try to develop tighter partnerships on that for being able to get back and forth to Mars more quickly. It's a nice resource to be able to have. So we're looking at developing some of those technologies. The moon is pretty far away, but it's close enough that in-space transportation with nuclear is probably not absolutely necessary for getting back and forth to the moon, but it is a nice thing to have for the Mars situation.
Okay, excellent, thank you. So we just have about probably a minute left. So lightning round question. You may have heard this asked to others before, but we'll go around the horn. Let's start with Mike. Mike, what's keeping you up at night?
Oh, that's a great question. What used to keep me up at night was getting stuck in a suit port where I couldn't get in and out of the vehicle, but through iterative designs, we actually have designed that with manual overrides and so forth. And we'll need to continue to do that to make sure that that's safe. And that's probably one of the things that keeps me up at night.
All right, let's see, Ginger, if you're still on. Is Ginger still on? Yeah.
I am, and I guess I will answer that from a pretty programmatic perspective. We've made so much progress. Our partners are at an excellent place. We have other interests from partners that have not been in the current portfolio. And, we're severely budget constrained going into this full year CR. So we're right on the cusp of moving out. So from a project manager's perspective, budget and schedule.
There you go. All right, Michelle, real quick.
I generally sleep like a baby because, like I said, everybody else is doing the hard work for me here. If I do stay awake at night, it's worrying about keeping Mike and Christina safe out there. For us, it's not an abstract. It's not some generic astronaut. These are people that we know. So we take that pretty seriously. So I'd say that's probably the one thing that would keep me awake at night.
There you go. All right, Clive, your turn.
Pass. Next question. No, it's political will, and having a space program that changes on a political whim. So we end up going nowhere because NASA keeps getting new requirements to go somewhere different because that was the other party's destination, not this. And I think that we need to stay the course this time because it's an inclusive way of doing things. Is that it's the moon and Mars and beyond, and it's not or. And so I think it's the political will aspect. Budgets, that's for Ginger to worry about and people at NASA to worry about, and we can help. But I think the political will aspect is something that I hope doesn't make everything stop and go in a direction which means we're not going to go anywhere.
And Cleb, I would just add real quickly that new business models are needed. Costs are important. We need to control costs. We need to not be stupid about things. And we need to have new business models. That is probably more enabling than any single technology.
Gotcha.
Amen. Preach on. So,
Doug, unless there's anything else, we need to close this out and move on to our next one.
Nope.
Any last words, Doug? Okay.
Thank you.
Hey,
I want to thank the panel. They did a great